Hi, I'm Roland, and this is my assistant Isabel. Welcome to my spare bedroom / home office / daycare center. I'm with CCOM, the Center for Coastal and Ocean Mapping at the University of New Hampshire. Recently, I led a team from UNH to compete in the 2020 Virtual Ocean Robotics Challenge put together by Open Robotics, the Naval Postgraduate School, and the Office of Naval Research. Besides myself, this team consisted of Coral Moreno, a PhD student, and Val Schmidt, who leads the Autonomous System group here at CCOM. The Virtual Ocean Robotics Challenge is held in a gazebo-based virtual environment that recreates a harbor in La Spezia, Italy, and includes Cora, a virtual autonomous boat. Cora has 2 thrusters configured for differential steering and is controlled via a ROS interface. As for sensors, Cora has a GPS, a motion sensor, a pair of forward-looking cameras, a LiDAR, and a USB-L, which is used to locate an underwater pinger. Gazebo is a new tool for me, but I'll show you a little bit what it looks like. So here's Cora. This is what I mean by still figuring out how to navigate. We can see GPS antenna up there, cameras, LiDAR is up here, and if I zoom out, some of you might recognize this as La Spezia. The challenge consisted of 4 tasks: station keeping, which is holding a position and a heading; wayfinding, which is navigating to various waypoints; perception, identifying various buoys and markers; and finally, Gymkhana, which combined the above tasks to have us navigate gates, find an underwater pinger in an obstacle field, and station keep above it. We found out late about this competition and only had about 2 weeks to prepare. For this reason, our approach was to quickly adapt our existing autonomous framework, Project 11, when practical, mix in off-the-shelf ROS components, and glue everything together with a few custom ROS nodes. The first step was to adapt what we call a helm node that interfaces our system to the boat, allowing us to control the boat and receive position updates to display in our operator station. The CCOM Autonomous Mission Planner, or CAMP, is our operator interface. For the actual challenge, CAMP was not used as the boat has to accomplish the tasks fully autonomously, but for development, CAMP was used extensively. Here, I can show you how, using a joystick, we can control the boat through our framework and display the results in CAMP. So here we are seeing a nautical chart that we download from Open CMap, I believe, displayed in CAMP, showing La Spezia and the position of Cora. We're also seeing some of the targets seen by the LiDAR. Once we were able to control the boat, we needed to add a higher level interface. On our own boat, a Seaworker 4, we can provide a target heading and speed, and the boat's internal controller takes care of the rest. In Cora's case, we need our own controller. We also want to try MoveBase, ROS's navigation stack, which is new to us. That means we need a controller that converts twist messages, which are linear speeds and angular speeds, to thruster commands. I quickly put in place a simple PID controller to get us going, while Val worked on a deep learning-based controller. After a few days, the deep learning-based controller showed some promise, but was not yet as good as our PID controller. So we scrapped it for the moment, and Val then worked on refining the PID controller, adding a cascading layer, in order to try to deal with the boat's pesky tendency to not keep moving forward and aft separate from turning. Finally, Val worked on a dynamic positioning node that allowed Cora to station keep. Of course, the dynamics of the boat made it challenging to sit still and point in a given direction. We were not able to achieve a perfect result, but we did find a good enough solution. Here is a replay of one of the station keeping runs. Like I said, not perfect, but good enough for now. Our first stab approach for the wayfinding task was to go from waypoint to waypoint, station keeping at each one of them for a while, then repeat the cycle until time ran out. This was done in the order the waypoints were presented to us. An attempt by Val was made towards the end to implement a traveling salesman solution to optimize the order of visiting the waypoints, but we did not have enough time to include it in our solution. Fearing that the actual competition runs might place a waypoint behind an obstacle, we tried using Ross's navigation stack with mixed results. Ideally, the components of MoveBase would use the LiDAR to build a map of obstacles, or an occupancy grid, plan a path to a given destination, avoiding obstacles, and move the boat by providing twist messages while looking out for new obstacles showing up within the range of the LiDAR. Since MoveBase was designed for wheeled robots driving on solid surfaces that are pretty good at achieving the commanded speeds, it did struggle dealing with our not-so-perfect controller for a boat that tends to drift a lot. For that reason, we decided to control the boat ourselves while MoveBase still generated maps for obstacles and provided us with planned paths to avoid those obstacles. Here, we are seeing a replay of our first wayfinding run. Obstacles are not a factor in this case, and our strategy seems to work fine. Our second run did not go so well. It seems like the boat went around in circles at the first waypoint, but never decided it had reached it. Consequently, it never made it to the rest of the waypoints, and our score suffered for it. Let's zoom in here to see what's happening. Just going around in circles. Next came the perception task. Coral Moreno did an outstanding job at quickly collecting images of the various markers and buoys from the simulation, annotating them, and using them to train a neural network that did a good job identifying the markers. She used YOLO v4, and the plan was to use GPU-accelerated darknet using NVIDIA's CUDA architecture for speedy IDing of buoys. Unfortunately, technical issues prevented our solution from running on the system used for scoring. After much troubleshooting, we tried compiling darknet without GPU support, but the results were too slow to be useful. A fallback solution was quickly implemented that used OpenCV to emulate the darknet ROS node interface, but use a CPU instead of the GPU. The OpenCV solution was still slower than using the GPU, but using the CPU, it was faster than darknet and fast enough to be useful. Finally, the final task brings everything together. A Python script called the Task Manager was quickly put together to coordinate all the pieces we've seen so far to complete this task. Markers were identified and located, gates were detected, and a plan was made and executed to navigate through them without bumping into them. Once the exit gate was crossed, a path was planned leading to where the pinger seems to be located. Our solution was not perfect, but it was good enough. Our team achieved the best score, beating second place by nearly 1 point. I want to thank my teammates, Coral and Val, for all their hard work. Thank you to the organizers for putting this great challenge together. We've learned a lot and had fun doing so. Finally, I want to thank you for watching. If you have any questions about any of this, feel free to reach out to me. Oh, and if you want to see the source code to our solution in all its ugliness as quick prototype code, check it out on GitHub. Thank you and goodbye. Bye-bye. Want to say bye to the camera?